Hello, everyone, and thanks for joining us for Tech Tuesday. We're going to give the attendees a few more moments to join, and as they log on, we'll get started here pretty close to the top of the hour. Thanks again for joining us. All right, well, hello, everyone. It looks like it's the top of the hour, so we'll go ahead and get started. Welcome, and thank you for joining us for Tech Tuesday. This week's edition brought to you by Vic Myers Associates in partnership with Alta Data Technologies. My name is Ryan Christian, and I'll be our moderator today. Just a couple of housekeeping items. First, we have everyone muted except for the presenters, so if you have any questions, please feel free to use the Q&A section or the comment box. We're happy to answer those at the end of the presentation. Also, I will be adding the content used in today's presentations as PDF handouts inside of the webinar. You'll be able to download them there, as well as we will send out a link after the presentation with the handouts, as well as a copy of the video to all anybody who registered, and you'll be able to share that with your colleagues or review it at a later date. You can also see this content and more on our website at www.vicmyers.com. The tech topic today is fundamentals of 1553 data bus systems. Today's topic is presented by our panelists, Bill Stahl, Western Regional Manager for Alta Data Technologies. Bill started selling to the aerospace industries in the mid-1980s. He has a wide variety of experience encompassing components and controllers for 1553, motor and power, embedded computing, including single board computers and I/O, test and simulation products, and systems for avionics, space and telemetry in benign and harsh environments. From all of us at the Vic Myers team and from our local customers, thank you, Bill, for your time and your willingness to share your expertise today. We really appreciate you. I'm going to unmute you now and make you the presenter. You can share your screen, and I'll let you take it away.
Okay, thank you, Ryan. I'm going to share my screen now.
Looks good, looks good.
Okay, all right, thank you everybody for joining us today. As Ryan mentioned, I'm going to give you an overview of the 1553 standard. So without further ado, I'll jump right into it. Okay, so the outline is going to be as follows. I'll give you a brief chronology of the standard, discuss the physical layer and bus connections, and then get into the software layer, if you will, the protocol. And those topics will include the encoding, word type, terminal type, message types, redundancy, and then some advanced topics, as well as things to remember. So as far as the chronology goes, the main thing to keep in mind is that the standard was first released in 1973, and at that time was adopted by the U.S. Air Force for the F-16 aircraft. And in the years since then, it's been adopted by the Army and the Navy, and then later on by our NATO allies, and is in use today basically on every military aircraft in the inventory, and even some commercial aircraft, including the Airbus A380. So as you can imagine, when a standard first starts out, the attempt was made to capture everything that could possibly conceivably be covered by the standard. But as time went on, there became a need for the release of new versions or updates to the standard. So you're going to see things like, MIL Standard 1553A, 1553B, and then the Notice 1 and Notice 2. And those are just further refinements and adjustments to the standard. Today, virtually the majority of all the 1553 you're going to encounter is going to be the 1553B, Notice 2. Okay, and just a quick nod to the concept of testing. There is, and what was actually released with Notice 2 was the concept of standardizing the test plans or the test procedures. One of those is called the RT validation test plan. So it was first defined in Notice 2 and then refined later on. And I could speak to that later for you if anyone has any questions about that. Most recently, the Society of Automotive Engineers, or SAE, had taken responsibility for the standard. So it transitioned from a MIL standard to an SAE standard. That has actually recently changed. It's gone back to a joint management of both the DoD and SAE. That would be just frankly, just in the past year or so. Okay, so enough about chronology. The physical layer. I guess the thing I want to start out with is think of 1553 as you would Ethernet in a way. They're both networks. Okay, you've got multiple terminals connected to the network in Ethernet, and in 1553. You've got a physical layer, then you've got a protocol layer. So in the physical layer, we have a very well-defined and very specific standard. It is, as you see there, it's a twisted pair, shielded. The blue wire literally is always a blue wire, and it's always positive. And the white wire is always a white wire, and it's always a negative. These things don't vary, even depending on country. Blue wire positive, white wire negative. You're always using 78 ohm impedance and termination, and it's always a twisted pair with the braided shield on the outside. To get a little look at how the bus is connected or how terminals are connected, you look at this picture, which basically shows the concept of transformer coupling. In the days of old, when Ethernet first came out, there were no such things as transformers. Coupling was done computer to computer. And if, for example, you had someone on the network unplug their computer or their Ethernet port went down, it would actually bring down the entire network. That's not the case today with transformer coupling. You can basically have a terminal turned off or failed or what have you, and it won't affect the rest of the terminals or computers on the network, or in this case, the 1553 bus. Some of the rules of the road as it relates to the physical layer and the assembly of a 1553 network is you've always got to have the bus itself terminated on each end. So you'll see in the upper left-hand corner a 78 ohm terminator, and the corresponding right-hand upper corner another 78 ohm terminator. Those are always required at the very end of the bus. You can extend as many times as you like, up to 300 feet. But you've always got to make sure that you terminate at the end. As far as the connection of systems to the network, that is accomplished through the use of a stub. Basically just a cable going from that coupler to the attached system or computer or terminal or what have you. The maximum length for that is 200 feet, or rather 20 feet, pardon. Okay, so you're going to connect all of your systems to the network in this way. So some things to note about, now that we're done with the physical layer, we're talking about the protocol layer. Some things to note about the signal is it's a serial data bus. It's a megabit per second. It is self-clocking. The encoding is biphase Manchester 2 encoding. The communication style is half duplex, so that means there's only one talker at a time. And there's only 3 types of terminal allowed on the bus. One is a bus controller, the next is a remote terminal, and the last is called a bus monitor. Going down the line, word types, there's only 3 types of words: command words, data words, and status words. So we've got this terminal called the bus controller, and it is the only one that can send command words. It can also send data words. We also have the other terminal called an RT, a remote terminal, and it can send status words and it can send data words, but it cannot send command words. And then last of all is a terminal called the bus monitor, which actually doesn't transmit anything. It is, as its name suggests, a monitor only. Okay, so essentially the encoding is basically 20-bit times per word. Okay, we allow, or the standard allows, a minimum gap of 4 microseconds between messages. Okay, the rules for remote terminals or RTs is that they must respond to the bus controller or to another RT within 4 microseconds to 12 microseconds. And if 14 microseconds elapses, the bus controller will actually kind of declare a no response timeout. Okay, as far as 1553, the encoding of it goes, if you're familiar with non-return to zero or NRZL, you'll recognize this form right down here in the middle. You'll see at the top, we've got the 1 megahertz clock, so every bit time is shown with a transition. And at the bottom, we see the Manchester 2 biphase encoding. So just a little different than the NRZ. If you look at the 1553 waveform on a scope, this is what you'll see if it's a well-formed waveform, meaning if there's nothing wrong. So in this instance, you can see that this is a command word because the first 3 bits of sync show it starting high, transitioning to low, and that's classic command word sync pattern. And I'll show you what the rest of them look like momentarily. So if you see your 20-bit times up along the top register there, you'll see command word starts with that first 1.5 bits high, transitioning to low. You look down here for a data word, it's actually just the opposite. So you'll recognize right off the bat whether you've got a command word or a data word. And then you'll see below the status word is like the command word, starting high and going to low. So the rest after the 3 bits of sync is basically going to be data, if it's a data word, or the command coordinates, if you will, if it's a command word, and then status information if it's a status word. So looking at the command word, we've got the 3 bits of sync. We've got 5 bits for the RT address, the remote terminal address, and then a bit to declare whether it's a transmit or receive command. And then we have the sub address, which I'll get into further. If you look at the RT address, that's kind of like a IP address would be for Ethernet. And then if you look at the sub address, you're going to see that's kind of what a port number would be in Ethernet. Okay, so we've got IP address, RT address, sub address, port number. It's just a location in the computer, which is the RT. And then you've got a tally of the data words, basically just telling you how many data words are going to be involved in that transaction. Okay, the data word type of structure is very straightforward. Sync, 16 data words, and parity. Everything ends with a parity, as you can see. And then for the status word, again, the remote terminal address, always important, and then status field for that RT. Okay, so I told you before about the 3 terminal types. We've kind of talked about them a little bit. Let's go into some more detail. The bus controller. Okay, there is only one bus controller permitted on the bus at any given point in time. Only the bus controller can send command words. And then lastly, but not least, it initiates all messages with a command word, okay? But it may also send data words. So if a remote terminal or / computer on the network needs some data, the bus controller can send that as well. Okay, the thing to keep in mind about a bus controller is that while there can only be one bus controller active at a single point in time, there are multiple devices or computers on the network that can, at times, perform the role of bus controller. Okay, so just keep that in mind. The next type of terminal is a remote terminal. And essentially, there's nothing more than a computer or box, a device, what have you. Think of an RT, it could be the comms radio, or it could be the mission computer, or it could be the weapon controller, or the navigation system, or any one of the systems or subsystems that are used on the aircraft. Okay, so that's basically all falling under all those devices, computer systems, all are commonly known as RTs or remote terminals on the network. There's up to 30 RTs, 31 RTs permitted on the bus, and their addresses go from 0 to 30. Only an RT can send a status word, and RTs only transmit in response to a command word. Okay, so they can't just voluntarily go out and send anything on the network. Okay, and the command word has to be sent by what? A bus controller, exactly. Okay, and then bus monitor, again, is listening. Now, the bus monitor, frankly, can be any number of things. An example of what a bus monitor would be a data recorder or some other passive device that does not interact with the network or the bus, but just simply watches the traffic and records it, or what have you, but it doesn't interact. So the bus monitor function can actually be located in an RT. It could be an ancillary function of the bus controller, but logically it appears on the network as a bus monitor. Okay, so bus controllers, RTs, they can send different types of messages. Okay, so here's all the different message types. So you've got a bus controller to remote terminal, receive message. This is where a BC is telling an RT you're going to receive some information. You've got an RT to BC message, and that's where the RT is responding back to the bus controller. And then you have instances where you've got an RT to RT transmission, if you will. So the bus controller will initiate the communication, but then the RT will follow up by transmitting to another RT. Now, there's things called mode codes, and basically these are administrative codes used by the bus controller to perform different functions. And I'll show you what that list of mode codes contains in just a minute. But you could send a mode code from a bus controller with data. You could send with receive data and with transmit data. There's also broadcast messages where broadcast from a bus controller to an RT or to many RTs, RT to RT, and then broadcasting mode codes with and without data. Thing to keep in mind is the RT address for a broadcast is reserved, and it's always 31. Okay, here's the list of mode codes. Okay, so there are some that are required. You'll see the 4 of them here. Okay, so things like transmit status. Okay, transmitter shutdown, override transmitter shutdown, and reset the remote terminal. Okay, so these are things that all RTs need to be able to comprehend and adhere to if they do receive these mode codes. The rest of these are all used by the system designer, meaning the 1553 network designer, for various reasons. Obviously, you know, initiate self-test, that seems like a pretty good one, right? Or, you know, synchronize without data, or, you know, transmit bit word, or things of that nature. So as you can see, it's all rather administrative type of function. Okay, so this, what you're going to see here on this slide and the next few slides, is basically kind of the look at you know, various message types. In this instance, we've got a BC to RT message, so that's where your bus controller is sending a message to an RT. It's a command message. Okay. Now there's 2 buses. I'll get into the redundancy later, but there's a bus A and a bus B. One's primary, bus A, and one's secondary, bus B. I'll explain it again, as I mentioned, later on. But if you look at this particular message, you're going to see some timing information. You're going to see the inter-message gap time displayed up here. Okay, so that's the space between messages. And then you're going to see that this message is occurring on bus A, the command message. And this is where the fun starts. You start decoding right here. This first number here is going to be the remote terminal address. In this instance, it's RT number 3. And the next thing you're doing is you're telling that RT that it's going to receive. Okay, if there was a T, then the RT would be transmitting. But in this case, it's an R for receive. And the next is the location. Again, that port number or that subaddress is number 1. So we've got the RT address / IP address 3 receiving at subaddress or port number 1. What's it going to receive? 32 data words right there. Okay, and then here is the content of the data words. In this instance, you know, we've got a response time here, 7.7 microseconds. We've got a total message time of 685.7 microseconds. That's just really diagnostic. That's just kind of giving you some information about all this. But the meat and potatoes is right up here. So let's look at another message. Here's an RT to BC message. Okay, this one's happening on bus B, and we've got RT number 2 transmitting from subaddress number 2, 32 data words. That's RT to BC. All right. Next would be an RT to RT. Again, it's going to occur on bus B. And we're going to have basically two sections of this message. One is the receive, and the other is to transmit. So you got to tell an RT it's going to receive, and you got to tell an RT to transmit. So RT1 is going to receive subaddress 3, 16 data words. Okay. RT2 is going to transmit subaddress 3, 16 data words. And RT to RT transfer. And there you go. There's your data words right there. Okay. Next, getting into the mode codes. This is what they look like. Again, it's occurring on bus A. The mode code is basically synchronized without data. Okay. When it goes to number 1, that indicates actually that's broadcast out, and the RT, rather the subaddress 0 indicates mode code. So you're not going to see any data, obviously, because it's saying synchronized without data. And then here's some more. Okay, so here we're going to synchronize with data. Again, mode code 0. Okay, and RT5. Here's your data. So it just kind of continues on from here. Again, same type of information. Again, mode code, so the subaddress is 0. RT is 3 in this case. Transmit, command. Now here's a broadcast. Okay, so the number 31 indicates that that's a broadcast. So when you say RT address 31, it's going to all the RTs. They're all receiving it. Okay, and they're also, in this instance, receiving to subaddress 9, 32 data words. And then here's an RT to RT. So we've got, again, a broadcast, RT address 31, receive, subaddress 17, 32 data words. Okay. RT5 is going to transmit from subaddress 24, 32 data words. Just so happens here. Empty. Okay, and then here's a broadcast mode code. So the way to tell that is, again, here's a broadcast, RT address 31. Transmit to subaddress 0. Again, that's kind of like the broadcast address for all subaddresses for mode code. And then it just kind of progresses from there. So by now you should kind of get a hang of it, you know, whether it's a broadcast or a specific RT, whether we're transmitting and receiving, whether we're doing a mode code as indicated by the 0 or not, and then the data. Okay, so we were talking previously, let me just go up one. We were talking previously about bus A, you know, and I think there was mention of a bus B up here. Yep, bus B. Okay, so I mentioned it was primary and secondary and all that. So that kind of goes into one of the features of the physical layer of 1553, and that's redundancy. So back when the standard was being developed, one of the main ideas or the main concerns that designers had was to ensure the greatest likelihood of survivability. I mean, these are military aircraft. It's not unreasonable to think that they're going to encounter some resistance in the form of bullets, missiles, what have you. other things that might somehow degrade the physical aspects of the network. So the idea is you want to have redundancy. So if a bullet flies through bus A, you could still be transmitting and receiving all the traffic on the network. And so you'd have a bus B, and you'd have them sort of not right next to each other, but spread apart on the aircraft. And you'd also have all of your devices connected to both. Okay, so that's kind of the rule of the game here, is that you'd have everything connected to bus A and bus B. You'd have this redundancy so that if bus A was compromised somehow, then the traffic would be falling on bus B instantly. Conversely, if bus B went down, bus A would be responsible for the traffic. So here's some of the rules. Okay, today 1553 can be used in either a single bus or a dual redundant bus configuration. If you're using a dual redundant bus configuration, you've got the bus A primary, the bus B secondary. Rules for the bus controller are that it can send messages on either bus. Rules for the RTs are that it has to respond on the bus where it received the command message or command word. Okay, so you can't have a situation where a bus controller sends out a command message to an RT on bus A, and then that RT says, "Oh, okay, I'll respond to you on bus B." That does not work. Not permitted. Okay, and then another very important rule is you can't have traffic on both buses at the same time. Okay, so you're not going to broadcast on both buses at the same time. You're not going to individually address to an RT, on both buses at the same time. Okay, here's an example of what a single bus looks like, the no redundancy. You'll see that all the remote terminals have both an A and a B connection on them, as does the bus controller. So in this instance, we're just not connecting B. Okay. Now you see up here, we've got a terminator here for 78 ohms. And we've got a terminator over here, 78 ohms. So there's no more 1553 bus on either side of those terminators. That's it. It's only running horizontally between the two. And then we've got these transformer couplers. Okay. And again, we remember that if, for example, this RT breaks, it's not going to bring down the rest of the network because it's transformer coupled. Okay, we've got the bus controller connected. And again, the bus controllers can see, because it's a network, it can see everybody that's present on that network, just like these guys could. And if you had a bus monitor, you'd have another coupler, and it would be going off to a bus monitor, and it would be able to see all the traffic from everybody on the bus. Here's what a dual redundant bus setup looks like. And frankly, it's just a mirror image, except rather than using the A connection, we're using the B or secondary connection. And again, you can only have messages, you can't have messages flowing on both buses at the same time. But same deal, termination. These are physically and logically separate networks or separate buses. Okay, so some things to remember. 1553 is a 1 megabit serial data bus. Okay, you can operate it in either single or dual redundant configuration. It's always transformer coupled. Direct coupling should not be used, and that's it basically, well, there's a lot of reasons for it, but not the least of which is what I described earlier, where a system somehow goes out of service and could take down the rest of the network. So the transformer coupling is necessary. Now, the couplers may not always look like this box. Okay, or that picture that I showed you before. There are things called inline couplers, and they literally look like the 1553 cable with a little sort of a little bump in it, if you will. That is permissible. It doesn't have to be, used with a twin-axe connector. It's an inline. It's kind of prefabricated, and that's actually what's on board the aircraft because of size and weight concerns. Okay, the three terminal types, again, bus controller initiates everything. There's only one bus controller active on the bus at a time. Okay, only the bus controllers can send command words. Message can have up to 32 data words. Bus controller should allow 14 microseconds for the RT to respond. Okay, and then bus controller should allow for at least a 4 microsecond gap between messages. Okay, remote terminals or RTs. Again, they're the computers connected to the network, and they respond to commands from the bus controller. So one feature about RTs is only they can send status words. Okay. RTs must respond to the bus controller within 4 to 12 microseconds. Okay, you can have up to 31 RTs on the bus, and their addresses are 0 to 30. And if you remember from before, RT address 31 is always indicating the RT address for a broadcast. So it's not actually a physical RT 31. 31 just indicates that we're broadcasting to all the RTs, regardless of their address. And then each RT can have up to 30 sub-addresses. Okay, so that's 30 ports or sub-addresses or locations inside that system that you can address to. And then sub-addresses of 0 and 31, I mentioned 31, indicate a mode code. And then last but not least, the bus monitor only listens, it never transmits. And I gave you guys the example of a bus controller, or rather a bus monitor being something like a data recorder. Okay, so some additional topics or advanced topics related to 1553, bus controller implementations. So the bus controller can be used to schedule the message flow, if you will. So you can create minor frames and major frames and aperiodic messages. You can also orchestrate and execute message retries and error recovery. You can do conditional branching. You can do enabling and disabling of not-op messages. Okay, remote terminal implementations, mode code handling. Okay, so based on the built-in test word, bit word, vector word, etc. Use of status word bits, okay, to have it do special things. So you can use all these facilities, if you will, to perform specific tasks. There's a thing called MIL-STD-1553, and that is a very specific sort of power-up response and checking protocol, if you will, or sequence that's used by remote terminal that is located in the weapons door on the aircraft. So looking at the wing of the aircraft, it's got an air-to-air missile attached to it. There's the weapons door is what's used, or pylon might be another way of looking at it. MIL-STD-1553 is not just 1553. It has a 1553 interface to it, to the aircraft, but it also has very specific controls and procedures for powering up the weapon and then finally releasing the weapon. And then bus monitor implementations, for things like data processing, error checking, archiving, or it could be a backup bus controller. I think I mentioned that before, that you can only have one bus controller active on the bus at one given time, but that doesn't mean the bus controller function cannot be performed by either an RT or a bus monitor. And that is usually always the case, that you'll have other devices on the network that are capable of assuming the role and function of bus controller should the primary bus controller, one, be destroyed or disabled somehow, or two, need to go off and do something else so it can turn over control to another device. And there's actually a mode code for that called dynamic bus control. Okay, I do want to get back to one thing here. So the message scheduling and all these things are basically for the bus controller. This is where you have all these different remote terminals connected to the network, all these computers, and they're all providing data of various types and various frequencies and so forth. So, depending on the frequency of the data and the updates that are occurring, the frequency of the updates, the bus controller, and rather the 1553 bus network designer, is going to optimize the performance so that the bus is being used in the most efficient manner. So it's going to set up schedules using minor frames and major frames, where it's going to basically enable or request data and status and other information and transfers from the remote terminals on a kind of a scheduled basis. Okay, so we're not, say you have something like landing gear. Well, that only changes, when you make it go up or go down. It's not like something you need to check every, 10 microseconds or even really every second. That's something you don't need to waste bus bandwidth on checking, every 15 microseconds or what have you. Something else, like maybe altitude or engine speed or something else, might need to be checked a lot more often. So you want to be able to schedule, requesting status from that RT more frequently. So it's that type of thing that is involved when you're doing scheduling, message scheduling. Okay, just to summarize, the 1553 started first use 1973, adopted by the Air Force. The aircraft was F-16. It was basically a definition for a physical layer and for connections to the bus, defining that, and it also was defining the protocol layer, how these devices would communicate with each other. So again, specifying the encoding, word types, terminal types, message types, and redundancy. So we've got bus A, bus B, primary, secondary, and things of that nature. Okay, so things to remember: only one bus controller at a time, only 31 RTs. Okay, you've got mode codes, which are using a sub-address of 0. You've got broadcast commands, which are using an RT address of 31. You've got 3 bits of sync in the beginning of every message, and you've got a parity bit at the end. Those are common. Your data words are going to start out that 3 bits of sync. The first 1/2 bits low, transitioning to high, and your status command words will be just the opposite, starting high and going low. Basically, nobody, in terms of no RTs, will speak unless they're spoken to, or rather commanded to, by the bus controller. And the bus monitor never transmits anything. It's passive. It's just listening. So that is all I have on the 1553 side of things. I do want to run through something briefly for Alta in general. There we go. So what Alta makes are 1553 test and simulation products and embedded interfaces. So this is going to be a little quick run through of that. What makes Alta so special? So our technology, our product line, the features of our products, the support we provide our customers, and our warranty. So technology is basically Alta is the most current or the most fresh, new, if you will, designer of 1553 products. We're not reusing anything from the 80s or 90s. All of our designs are, circa, 2010. Okay. We don't use any third-party content like chips for our 1553 or ARINC 429 functions. We actually developed our own 32-bit protocol engine, and we instantiate that in an FPGA, such as a Xilinx. So we own the recipe and really control our destiny as it relates to our 1553 specific product content. Okay, as well, all the firmware and software that we provide was developed in-house. And we developed a couple of things, invented a couple of ideas, such as the common data packet, which basically the idea here, or the revolutionary idea here, is that we have one data structure for all BC, RT, and bus monitor data buffers and ARINC 429 label types. Okay, so believe it or not, competition has separate data structures for all these different things, and that becomes kind of cumbersome and difficult to work with. Our API utilizes or is based on an OSI model design, okay, which is abstract and portable. What I mean by that is you don't have to worry about any of the machine level stuff. You don't have to worry about really even anything except for loading the right API for your version of software, whether it's 32-bit Windows 7 or 64-bit Windows 10 or 32 or 64-bit Linux or what have you. That's all you have to worry about. The rest is taken care of for you. Okay, we have, for example, our products. Another feature is the built-in test. We've actually got 3 different types of bits that are performed on the product, or the product is capable of performing, as well as a transmit loopback. And then we have dual temperature sensors on all of our products that we monitor. Looking at the technology, I mentioned this common data packet. Okay, here's just kind of an eye chart of what it looks like. There's a bigger picture in our manual. I'll be happy to share with you. Then the API, which I mentioned before, with the OSI model and the abstract layers. So basically, everything layer 0 on down, you don't have to worry. So you don't have to deal with the OS specific stuff, or the device specific, or even the backplane specific. You would just encounter our API at this layer 1, and at that you would receive a nice library of over 100 pre-programmed and pre-tested sample programs that you can use. It's all written in C, and you can do with what you will. Or you can use our application called AltaView to control the 1553 cards. Next thing is our product line breadth and depth. We basically have probably the most number of variants of our products, if you will, for the different host computer bus interfaces, whether it's PCI or Express Card or PC104 or Mini PCIe, XMC, what have you. Then we also have our devices, such as Ethernet, Thunderbolt devices, and super speed USB 3. Okay. So we just keep on developing, and we specialize in 1553 and A-Ring 429. So that's got our full attention. So we're not doing serial I/O or RS-422 boards, or single board computers, or even systems. We're specializing just in these two avionics buses. Okay, some of the features, RT validation. I think I mentioned that on one of the first slides, the RT validation test plan. We actually have all of our boards, or rather the majority of our boards, have the ability to run the RT validation test plan that was specified by the SAE. And so the engineers that are trying to develop an RT can go ahead and do that, and then run our validation test and get a sense of whether their RT complies with the standards or not. And we have other features. One thing that RT validation test plan requires is variable voltage. Okay, we do, although it's not recommended, and we don't usually sell it. We do support direct coupled connection to 1553, although most of it's done through transformer. We have a feature on our products called the signal generator and the signal capture. Signal generator, as you might imagine, allows you to create a 1553 waveform. Signal capture is basically an A to D on in the front of the first channel of our 1553 device, and allows you to capture the waveform, like I showed you during the 1553 class. We also have other features like an NVRAM write disable. This would allow you to bring your Alta product in like a classified area and be able to take it out, because we would not allow any writing. We actually would inhibit or disable the ability to write to the memory on the card. We also have a transmit inhibit. We also offer extended temperature range products, conduction cooled consideration, as well as conformal coding. And then I mentioned support. Okay, so first of all, there's no cost for our firmware and software updates for the life of the product. There's no cost for unlimited email support or phone support. There's no cost ever for our API, which includes the Windows, the Linux, the VxWorks, what have you. There's no cost for the library of 100+ example programs that I mentioned to you. And then finally, no cost for the AltaView software for Windows, which allows you to monitor 1553. So it's a Windows application. There are things that you can purchase to go along with AltaView that allows you to do simulation and recording and some more advanced features, but the basic monitor function is free of charge. Okay, it also allows you to program the card. And then last but not least is the quality and the warranty. So basically 5-year warranty. Okay, it's the longest one in the business. Quality, okay, ISO 9001. We've got ESD program, ANSI certified. We got over 40,000 products shipped since 2010, and a very small manufacturing failure, as you can see. We utilize JTAG boundary scan, so we're really able to weed out any failures way before we ever even ship them. And last but not least, we've not charged for a repair yet, and we have not end-of-life any product. Okay, so just to summarize, latest generation of avionics analyzer using full .NET and ribbon bar GUI technologies. We've got an XML setup and schema, so it's easy to use, easy to edit and import and export. Easy to use GUI controls. This is all relative to our AltaView. We've got the signal capture and the engineering unit conversion built in. Okay, so there's no separate thing you have to do to EU convert your your raw hex data. And then last but not least, you can load AltaView on all your machines for free and do post-analysis, again, free of charge. And that's pretty much it. So I'll kick it over to you. Oh, Ryan will take it over here.
Thanks so much, Bill. I appreciate you going through all that. Everyone, I'm going to give you a few minutes here if you have any questions. I do have a couple that have already come in, Bill, that we can answer while anybody thinks of any questions they may have. In addition, the first one was specific about in your training, you were talking about bus monitors. Does the bus monitor require an address?
Okay, hang on 1 second here. I'm just losing. Okay, can you repeat that?
Does the bus monitor require an address?
No.
Okay.
Again, it does not appear on the bus. So there's no address.
Okay. What kind of computer should I use with Alta products?
Well, any x86 processor will do. We don't support ARM processors, but we do support any of the x86 Atom family. And then we support all the different operating systems, be it Windows, Linux, VxWorks. And others. I'm getting a little feedback. Are you getting that as well?
I'm not hearing it, Bill. I'm not sure what it might be if it's coming in on your end. Right. Hopefully the audience isn't hearing it, but I'm not. Last question I have here is about programming. Which of the software is used for programming?
Which of the software is used for programming? Okay, if you want a Windows application to program our products with, that is AltaView. And that is the one I was referring to. It's actually a free download from our website, and you can use that for basically doing 1553 monitoring. You can then do things like, set up simulations and set up recordings, and also view the data during playback or live. And then if you don't want to use that, we do have the sample programs. There's over 100 of them written in C that allow you to do the same thing, basically anything that the card or device can do. We have an example program that you can run to do that. And what's nice is a lot of our customers will take those example programs and basically incorporate them into their test software that they're developing. We also support LabVIEW if people would prefer to use LabVIEW. We have all the VIs for all of our products as well.
Okay, I think that about wraps it up, Bill.
All right, well, thank you everybody for your time.
Yes, indeed. Thank you all for joining us for Tech Tuesday. Sorry about some of the audio feedback, and we look forward to catching you next week for Tech Tuesday. Everybody stay safe out there. Bye now.